Hi, this is Jeffrey. Welcome back. And the topic we're going to be discussing today is complex numbers. Here's the learning objectives. So in this section, you'll learn to add, subtract, multiply, and divide complex numbers, as well as simplifying powers of I. Before we get into the adding and subtracting part, we will first have to note this, like what is complex number. So a complex number is a number of form a plus bi, where a is the real part of the complex number, and b is the imaginary part of the complex number, like here. The 5 is the real part, the imaginary part is the 2i, where there is a like I after the number. So yeah, if b is equal to 0, then a plus bi is just a real number. And if a is equal to 0 and b is not equal to 0, then the complex number is called a pure imaginary number. An imaginary number is an even root of a negative number. And also, like here, we have to first know that I is equal to the square root of negative 1. And so, if we square these on both sides, like we get I squared is equal to, cancel out the square root sign, so we get negative 1. So we get like the square root of negative 1 whole thing squared, we get negative 1 here. And if we like do like let's say I cubed, we'll get negative I, because like I squared times I, so we get negative I. And if we do like I to the power of 4, we'll get negative 1 times negative 1, which will just give us like positive 1. Alright, the next one, we'll have to know how to plot a complex number on the complex plane. So we cannot plot complex number on a number line as we might real numbers. However, we can still represent them graphically. To represent a complex number, we need to address the two components of the number. We use the complex plane, which is a coordinate system in which the horizontal axis represents the real component, like here, and the imaginary part is the vertical line. Yeah. Complex numbers are the points at the plane expressed as ordered pair A, B, where A represents the coordinates of the horizontal axis and B represents the coordinates for the vertical axis. Like, if you look at this example, negative 2 plus 3i, we'll notice that like the real part, the horizontal line, is negative 2, and then the 3i belongs to the vertical part, the imaginary part. So we'll just put it like negative 2 and then go up 3. So this is how we plot a complex number on the complex plane. Yeah, so let's get into the adding and subtracting complex number part. So this is pretty simple. So we first just have to identify which one is real and which one is imaginary, and then we separate them. So let's see this one. A plus bi plus c plus di. So like these two are like terms, we can add them together so we get a plus c, and then we got the like terms right here, so plus bi plus di, so b plus d whole thing times I, right? Same with subtracting, we'll have to first identify the like terms, so again a minus c and then bi minus di, so b minus d whole thing times I. Yeah, that's for the adding and subtracting part. The multiplication and the dividing part is a bit harder, but still, let's take a look at this, right? So let's begin by multiplying a complex number by a real number. We distribute the real number just as we would with binomial. Like for this example, we got like 3 times the whole thing, 6 plus 2i. So basically just distribute, right? So 6 times 3, and also 3 times 2i. And then we simplify it, so we got 18 plus 6i. And then we got a second one, multiplying complex number together. In this case, we don't got like a real number up front. We got two set of complex numbers. So now let's multiply two complex numbers. We can use either the distributive property or more specifically the FOIL method, because we are dealing with binomials. We call that FOIL is the acronym for multiplying first, inner, outer, and last term together. The difference with complex numbers is that when we get a square terms I squared, it equals to negative 1. So let's look at this example. A plus bi whole thing times c plus di. Right, so again, we'll do the FOIL method. a times c, a times di, bi times c, bi times di. So we got AC plus AD times I plus BC times I minus BD. Notice that the plus sign turns into the negative sign and the I squared cancels out since I squared is equal to -1. So that's how it turns into this one. And then we just like regroup the whole thing. So we got AC minus BD plus AD plus BC whole thing times I. That's how we do the multiplying of two complex numbers. Alright. Dividing complex numbers. Dividing two complex numbers is more complicated than adding, subtracting, or multiplying because we cannot divide by an imaginary number, meaning that any fraction must have a real number denominator to write the answer in standard form a plus bi. We need to find the term by which we can multiply the numerator and the denominator that will eliminate the imaginary portion of the denominator, so that we ended up with the real number as the denominator. This term is called the complex conjugate of the denominator, which is found by changing the sign of the imaginary part of the complex number, like this one. The complex conjugate of a plus bi is a minus bi. Like for example, the product of a plus bi and a minus bi is this. Right, since like the I squared will turn into -1, so which leaves us just with a squared plus b squared, and there is no more imaginary part, right? The result is a real number, yes, because there is no I. So now that the complex conjugates have an opposite relationship. A complex conjugate of a plus bi is a minus bi, and a complex conjugate of a minus bi is a plus bi. Further, when a quadratic equation with different coefficients has complex solutions, the solutions are always complex conjugates of one another. Continue here. Suppose we want to divide c plus di by a plus bi, where neither a nor b equals to 0. We first write the division as a fraction, then find the complex conjugate of the denominator, then multiply. So c plus di over a plus bi, where a is not equal to 0 and b is not equal to 0. Multiply the numerator and the denominator by the complex conjugates of the denominator. So right here, the denominator is a plus bi, so the complex conjugate of a plus bi is a minus bi, right? And this whole thing is just 1, so it will not change the result. So yeah. Once we do the multiplication, we start like using the distributive property, right? We got like I squared on top and I squared on bottom, and the negative ABI plus ABI cancels out. So which leaves us just that like no imaginary part at the bottom. So CA minus CBI plus ADI minus BD times -1 over a squared minus ABI plus ABI minus B squared times -1. And we can like cancel out the -1 on top and on bottom. And also this part, right, negative ABI plus ABI is just 0, so we got real number on the denominator, and our numerator will become CA plus BD whole thing plus AD minus CB whole thing times I. And that's our solution. The last one, simplifying powers of I. So the power of I is cyclic. Let's look at what happens when we raise I to increasing power. So I itself is just I, right? And I squared is -1. Recall that I is equal to the square root of -1. So I squared is equal to -1. And I cubed, which is just I squared times I, will give us -I. And I to the power of 4 is I cubed times I, which is just like which is just -1 times -1. So we got +1. And if we got to the 5th power, it gives us just 1 times I. So that's just I again. And then if we keep on doing, we'll notice that there is a pattern. So like I to the power of 6 is equal to I to the power of 5 times I. So again, we got like I squared. So it's I to the power of 6 turns into -1. And the pattern keep on going. So we can see that when we get to the 5th power of I, it is equal to the 1st power. As we continue multiplying I by increasing powers, we'll see a cycle of 4, and that's examine the next 4 powers of I. So notice that I to the power of 6 is equal to negative 1, right? Negative 1. And I to the power of 7 is equal to negative I, right? Negative I. And then I to the power of 7, I to the power of 8 is equal to 1, 1. And I to the power of 9 is equal to I, again. So yeah, there's a pattern, like cycle of 4. So the cycle is repeated continuously, like I, negative 1, negative I, 1, every 4 powers. Yeah. And that's it. So let's do some practice question. Adding and subtracting complex number. So add or subtract as indicated. Question A, 3 minus 4i plus 2 plus 5i. Question B, negative 5 plus 7i minus negative 11 plus 2i. And I'll give you guys 30 seconds to work on this, starting from now. Alright, here's the solution for number 1. For question A, it's basically just like distribute the like terms, right? So 3 plus 2, we got 5, and negative 4 plus 5, we got just positive ones, which is just I. Alright, for question B, it's harder because we have to distribute this negative sign into that, so we got negative 5 plus 7i plus 11 minus 2i. So negative 5 plus 11, we got 6, and 7i minus 2i, we got 5i, and that's our solution. Alright, practice question number 2. Multiply a complex number by a complex number. So multiply this one. 4 plus 3i times 2 minus 5i. Again, I'll give guys 30 seconds to work on this one, starting from now. Alright, here's the solution. We basically like using the FOIL method, so 4 times 2 plus 4 times negative 5i plus 3i times 2 plus 3i times negative 5i. So we got 8 minus 20i plus 6i minus 15 times I squared. Notice that I squared is just negative 1, so it turns this negative sign into a positive sign. So 8 plus 15, we got 23, and negative 20i plus 6i, we got negative 14i. So the solution is 23 minus 14i. Alright, the last practice question, simplifying the powers of I. So it evaluates I to the power of 35. I'll give you guys 20 seconds to work on this one since it's, I'll say easier. So yeah, 20 seconds starting from now. Right, here's the answer. Since I to the power of 4 is equal to 1, we can simplify the problem by factoring out as many factors of I to the power of 4. as possible. So to do so, first determine how many times 4 goes into 35. So 35 is equal to 4 times 8 plus 3. 4 times 8 is equal to 32. So 32 plus 3 is equal to 35. So I to the power of 35 is equal to I to the power of 4 times 8 plus 3. So I to the power of 4 times 8 times I to the power of 3. So this whole thing right here is just 1. So we just have to know what is I cubed. And I cubed, we know that it's negative I. So that's our solution right here. And that's basically all for today. Thank you.